Welcome to CIE101 Civil Engineering Graphics. My name is Claude Junkins. This is a week one lecture on what we're going to be doing this semester. We're going to learn graphic communications using AutoCAD products, Autodesk products. AutoCAD 2014 and Revit 2014 will be used this semester. Probably the first half of the semester will be basically fundamentals of AutoCAD 2014. The textbook we have is specifically for civil engineering fundamentals. The second half of the semester we're going to work on Revit, which involves BIM, or Building Information Modeling, to a certain extent. Again, we'll be working on the fundamentals. So to start out, we're going to talk about one of my passions. I've been doing this type of work for about 35 years now, starting out as a board drafter and turning into the CAD software. Later on, my expertise is more in MicroStation. I'm kind of a newbie when it comes to AutoCAD. I've also taught Solid Edge to mechanical engineering students, which worked out pretty well last year. It was as much a learning experience for me as it is for them. We'll go over the syllabus in a little bit. The slide that you see in front of you is a cave painting from back in the prehistoric days, and I bring that up just because I think it's important to recognize that it's a picture's worth 1,000 words in most cases. It's much easier to recognize an image and extract it from nature or something you've seen, as opposed to trying to read and disseminate a drawing, or a text file, I should say, or specification. We have a lot of graphics out there. Some people are what we call dyslexic when it comes to reading. I suffer a little bit from that myself, in that you can read something and 5 minutes later you wouldn't be able to recognize what it was, but if you draw me a picture or show me an image, then that kind of sticks with me a little bit more. There are other people, some of which may be in this class of 92, who are what I refer to as graphic dyslexia. They have just the opposite. They have trouble visualizing something that's drawn in paper. And we work in, when we look at a computer screen or we draw on a piece of paper or vellum, we look at things in a two-dimensional way, XY coordinates to be exact. If we look at the picture of this person's face, we see that we have an X coordinate and a Y coordinate. We have positive and negative numbers. I don't show the negatives here because basically when we're working, we don't really think of things in negative or positive, but you can see that this individual's picture, two-dimensional picture, is on the screen, has XY coordinates. And if I were to trace lines around this object, each of these points of that line would fall on an XY coordinate. So if I've traced this face out in red with a pen, I've basically given it coordinates, and then I can delete the picture and I'm left with somewhat of an image. This blue box on the outside is what we refer to as a plane of projection. This is the flat, no depth plane, just like a sheet of paper, but even thinner, has zero depth, that allows me to outline this in a two-dimensional format to give me the view of that person. But I'm only able to see the front view. If we're to look at the side view of that same individual, suddenly we still have an X and Y coordinate, but it just shows up as this thin line, but we've added the Z-axis in here, this third dimension, so to speak. So the third dimension gives us a side view of this person. Again, if we outline it this time in green and we remove the picture, we're left with a side profile. So by looking at the front profile that we saw previously and the side profile, we start getting a visual image of what that person might look like. Now if we take it a step further and we put this individual in a glass box. Now the box has 6 planes of projection. It has a top, it has a bottom, it has a front, it has a left side view, a right side view, and a back view or rear view. Within this glass box or cube lies points, as many as you can imagine, depending on what scale you're thinking about. This could be 2 millimeters, could be 2 inches, this could be 2 feet, this could be 2 miles, this could be 2,000 miles. It all depends on what your scale is, and we'll talk about scales a little later on. If we're to take that person and put them inside this glass box, just their bust, their shoulders up view, suddenly we can look at this person and we can see that plane of projection coming to the front, coming to the side, and this is what we refer to as an orthographic projection. We could trace this person out on all 6 sides of the orthographic projection, and if we unfold that box so that everything lines up, the top view would show the person. If I folded this up, I'd see the top of the person's head up here, the front. If I pull this out flat in this direction, just imagine this is a hinge and we open this flap up, we'd have the right side view, the front view, and the top view. Suddenly we're able to look at a top, front, and right side view on a single sheet of paper or a computer screen and see that we can visualize what this person might look like. If I take it a step further, this is an Adobe 3D view. We can look at it from different perspectives now in the 3D model so that we can kind of see, there's our back view, our right side, our left side. We want to look at it from the bottom, so the computer gives us the ability to look at things from many different angles, even perspectives. We can change the lighting on her. I don't know whether there's no lights. Let's see. I think we can change her to a transparent view. We can look at the shaded illustration, which is what I just had, or just an illustration where we can just look at a line drawing of that person's 3D model. This is just a perspective projection, so you can give her a little bit more depth. So there's a lot of ways that we can look at these things. And again, we need to think about scale. And I like to bring up my favorite character, Horton, the Dr. Seuss character, Horton Hears a Who. And I think of Horton when I think about scale. Horton finds a society living on a dust speck, on a clover that he picks out of the ground, and he can hear them because of his big ears. And if you think about that just a little bit, we've all, thinking about universal space and whatnot. We can scale things up and down as much as we want. If I wanted to show what that society on Horton's dust speck on his clover looked like on a sheet of paper, I could scale them up 10,000 to 1 or 20,000 to 1 in order to make them big enough to be seen. And just like the animators did in the movie, they're able to scale him up or down. So as we talk about scale, if I wanted to show the floor plan of Boardman Hall on a sheet of 8.5 by 11 paper, I can do that. But we have to think about scaling it down and being able to work with our scales. And when I talk about scales, I'm talking about the physical rulers, the that we think about, the scales, the three-sided scales that are set up for engineering and architectural and mechanical drafting, so that if it says 1/4 inch equals 1 foot, we have a scale, we can lay it on the paper, and we can determine that the length of this room is 35 feet. We can we can determine square footages and things like that from the computer. So one of the things that in the past teaching classes such as this I've found is that some students have a difficult time wrapping their heads around the whole idea of 1 inch long on a piece of paper equaling 500 feet in real life. So we need to really get that simplified and down to the point where when you look at it, you're just going to recognize it. And I have a tendency sometimes, if I've been criticized in the past for my teaching methods, it's been for going a little too fast. And I agree with that in a certain extent, because it's important that I try to get things out. But when you've been doing things for 35 years or so and things just tend to come naturally, after a while I don't think about the fact that maybe some people in the class haven't had the exposure to the type of things that I'm talking about. So if I get going too fast or things aren't making sense, be sure to see me about it. And again, we'll go over more of that when we start talking about the syllabus. One of the big things in drawing on paper or on a computer is that line weights are particularly important. This chart, and I'll make this available on Blackboard to everybody, gives us a layout of line weights that are there. This is basically just the chart. It gives us to us in millimeters and inches, and this is a 0.002 inch line would be something like this, 0.05 millimeters. And when you think about this, think about when you buy a mechanical pencil, one of those push ones. 0.05 is kind of the thin one. I have difficulty using them myself because I've got hands like bear paws, and I tend to break the lead quite easily. So I go to a 0.09 millimeter pencil, which is a little bit thicker. In comparison to the 0.3 millimeter line, or 0.1012 inches, would be similar to a 2H pencil. When they tell you to take your test, fill in the bubbles with a number 2 pencil. That's this pencil lead softness here. If you really want to make dark, heavy lines, the 0.60 or 0.024 inch line weight, size 2, would be your H, F, and B. And this is lead that's more like charcoal. It just melts off the pencil. So, but it gives you very, very dark line weights. If we look at our next slide, we see our United States National CAD standards for plotting guidelines. Our line widths for extra fine, fine, thin, medium, wide are all listed out here, and again, I'll make this available to you. We also need to be looking at line styles. And you can see by this drawing that we have a number of different line weights, and we have line styles. The dimension line, for instance, is a thin, dark line, 0.3 millimeters. The phantom line, 0.3. When we get to our solid lines, they're 0.5 millimeter. If we get to our visible lines, this is a note, 5 millimeter. The visible lines or solid lines are 6 millimeters. Our short break lines are 6 millimeters. They're nice and dark, so you can see the contrast. When we look at this drawing, we can tell what's physical. This armature is shown with this center line that says it can pivot 90 degrees vertically, and it shows us this phantom line or ghost line that says this is what it would look like when it's vertical. It gives us dimensions. It gives us this cut line. Notice how dark this is. This is a 0.6 millimeter, and I might even go a little darker than that on a section line. It's saying I'm going to cut a section through this arm, and what I see would be shown down here. You can see AA matches up to section AA here. Gives me a cross section with this hatching in it that lets me see what the profile of that arm looks like, because this is the only way to visualize that. If I were to turn this to a front view, a right side, bottom up, I wouldn't be able to tell what the actual size of this is, because it's always going to be hidden behind these objects in any particular orthographic view. So down below we have our line styles, which is a visible thick line, 6 millimeters. Hidden lines, which are dashed lines, 0.3 millimeters. A cutting plane line, I believe that's 0.5 millimeters. I think that's, I'm having a little trouble reading this. I'll blame it on my double vision glasses, but the clarity isn't good. It's between 6 and 8 millimeters. We'll print this out again and have it ready for you. These break lines, or if something's too big to fit on the paper, we'd use something like this. Your center lines, they're dark but they're thin. Your dimension lines are dark and thin. Section lines, your phantom lines, you can see the stitching lines, the symmetry, the chain lines are all line styles that we might use. For civil engineers, we also use something called custom line styles. And custom line styles are designed for use on underground utilities. I'll show you an example in our labs of our campus maps, which show where all the underground utilities. So if something like a gas line would show up as a long line with a dash and then a G in it and a dash and another long line, so that repeats itself throughout. So when we look at our map, we can tell exactly where all of our utilities are underground and what those utilities are by just the designation on the line style. I've included this this manual that I stole from the web. It's the Harvard University Planning Office. I like to go Ivy League whenever I can. We're going to look at their CAD standards, which I think is probably a pretty good device. Whenever this university looks to have something done on campus, they want the architects and engineers and contractors to supply the information to them in a particular way, so that every time they put an addition on a building or build something new or do a renovation, the documents that they receive in the end, and this gets back to the BIM process, are all the same. And this includes line styles, and it includes layers. When we talk about layers or levels within a CAD environment, if we were to compare CAD layers to what we did when we worked on the drafting board with a pencil or a pen, it's what we would call a sepia print, or just a tracing print, where you would put the basic floor plan on a sheet of heavy vellum, something that of good stock, and that would be your base drawing. When you get ready to add things like furniture, you'd put a piece of tracing paper or vellum over the top of that, tape it down, and draw all your furniture on that piece of paper. And then you could run both sheets of paper through the blueprint machine at the same time, and you'd come up with what they call a sepia print, which was kind of faded, didn't really look all that great, but it worked. And you could do the same thing with your electrical plans and your plumbing plans and your telecom, your HVAC. All of those things could be overlaid on sheets of tracing paper and run through simultaneously, so you got a combination drawing of all of those things lined up together. And we used to see these printer's marks on the drawing, so that you made sure that everything lined up properly when you ran it through the blueprint machine. Well, with the advent of computer-aided design and drafting, we've developed, or I haven't, somebody has developed, the ability to put things in specific layers. And the American Institute of Architects has expanded that to no end, and we'll look at that here in a second. I brought Harvard's document because it's a little less imposing than the AIA documents. If you look up on the web AIA layering guidelines, it's a 100-page PDF document on how to name layers in a drawing. The ability to create specific layers for specific items in a drawing allows us to do the same thing that we did with solid paper and tracing paper on the drafting board, in that we can turn those layers on and off. I may put all my exterior walls on one layer, and all my interior walls on another layer, and all my doors on another layer, all my windows on another layer, all my bathroom fixtures on another layer, kitchen fixtures and furniture may be in a different layer. The ceiling grid patterns for suspended ceilings would be in a different layer. Telecom information, all of those things that would show up that you may want to, and in many cases you do want to, not show those on every drawing. I want to have my floor plan with just my electrical layout printed out, my floor plan with just my HVAC printed out. But I also want to see all those things together so that I can determine if we have something called clash. Clash detection in software says, hey, you got a water pipe running through your warm air supply. You need to fix that. And again, that's where we get into BIM and 3D modeling so that it helps us get through those things. But sticking with just 2D, you can see that Harvard University wants their file format and setup done in electronic, meaning it's a CAD file. They have specific scales, units, and tolerances, fonts and text styles, title blocks, use disclaimers, policy on model space and paper space, standard layering list. These are all included in here. So they give, oops, went too fast here. I'll skip through that. File format for quality assurance. These are all things that need to be checked off by the architect. That they've looked through this and they're matching up all of this. And in the case of our university, one thing I don't see anything, well, they say floor and building and floor identification codes. That kind of goes standards, but I'm also would want to include room numbering. Why can't I just go through and number a building however I want? As an architect, that's fine. But when it gets onto a campus like the University of Maine or Harvard University, it becomes difficult if those room numbers are also tied to your space inventory. Believe it or not, our space inventory, where people are on campus, what they're doing, has a financial impact with something called indirect cost recovery for federal funding. So it gets kind of like the IRS. It becomes very difficult to maintain. So we have certain standards that we need to stick to make sure that we know that what's being done in that room is laboratory work, or what's being done in there is office space or grad students, or how that space is being used has a direct impact on federal funding to the university. So we need to keep close eye on it. So those things are important. If an architect numbers a room or a building and it doesn't fit our standards, when we have to renumber it, it also affects 911. If the alarm system has already been set up for the room numbers that the architect has put on, and we go and change the room numbers, then all of a sudden when an alarm comes into the fire station or the police station, they get a room 100, they go over and they find out room 100 isn't there anymore, it's been moved somewhere else. So we start getting nice little emails and letters. They talk about the electronic file format here. Facilities, documents, drawings, and construction project drawings must be submitted to Harvard University in full compliance with AutoCAD 2004 with a DWG extension. That is the standard file extension for AutoCAD. AutoCAD will read some others, but the most popular one used is DWG. All CAD drawing models should be drafted at full scale in architectural units such that one drawing unit equals 1 inch. Meaning that we don't want just sheet files sent to us, we want to actually have the full-size model. When we draw in CAD, we draw everything to full scale on the computer. And then we scale it down when we get ready to put it on what's called a sheet file or a draft file. The rest of the stuff, XREFs are always a problem when we get them in ourselves because they never actually show up correctly, so it's nice that those things are all exploded. Now here's our layering. You can see it's pretty extensive, and we start here with architectural layers. We won't go through all of these, but they give us information that says the A annotation text, this is just general text on the drawing, is drawn in this level. It's actually created. It's color 4, cyan. Doesn't give us a line weight, but we can come up with that. And it is continuous line type. Our red lines are just a layer where somebody would go in and make notes for corrections. Annotation symbols, annotation legend. Down further we get into architectural door. Doors are going to be drawn in color 2 yellow in a continuous line style. The door identification, the number on the door, would be continuous. It doesn't really give us a color. So that's kind of, these are just the standards, so I guess you can use what you want. A ceiling is a layer. Let's get down a little further. These are all, there's one for elevators, stairs, glazing, windows, walls, partitions, a roof level, a wall interior, a wall exterior, full height walls, firewall patterning. This is just the patterning that goes on interior walls that might be a firewall. So all of these things, there is an A wall general. So you can take this level structure and make it as big or as small as you want, but it should match this standardization. Everybody in the industry, no matter what software you're using, is trying to maintain this. Now we get down into the civil leveling, we can see that there's a level for parking, property lines, property bearings and distance labels. General text again follows the same thing, but it's got a C annotation in front of it, meaning it's part of the civil drawings. Fire protection, you can see that we also have layers for fire protection. We have layers for interior equipment and furniture. We have layers for mechanical equipment, everything from low voltage wiring to compressed air piping. We have structural layers in our drawing for steel beams and girders and columns. They're all included in here. So if you're going to draw a column on a floor plan, it needs to be in this S columns level, because there may be a time when I want to turn those columns off so I can see what the floor plan looks without them. Column grid, something you see on a floor plan which shows where things are, and when we look at our drawings that we're going to have as part of our package for the Recreation Center and the Milford Bridge, I've got some others I'll be bringing in, we can see a lot of these things on them, and I'll also try to bring in some drawings that we've gotten from architects that are drawn to this level specification, so we can start, you know, it's great to go in and be able to tear somebody else's stuff apart so we can actually tell what's going on. Here's some university notes with regard to room numbers. Layer name formatting is listed up here, status field. They give us a preferred CAD vendors producing facilities drawings should consult your Harvard representatives for preferences. Pen number 1 is red, has a line weight of 0.010. All the way down to pen number 50, which is tan, has a weight of 0.035, so that's just extremely thin line weight. So they give us a list of line weights, and we may use some of that. Now, went a little too fast. File naming conventions. They give us, they want their building code. So the building happens to be 4557 as the root, and they use a hyphen or an underscore, 01.dwg, and this happens to be the first floor. -1 is the basement. But if we look down here, you can see that they're also using naming the construction drawings. So your drawings in your package that you see have an A for architectural, C for civil, E for electrical, F for fire protection, G for general, H for hazardous materials, I for interiors, L for landscape, and then it will be floor plan or -FP1, FP2, FP3 for whichever elevation you're going to be on, or site plan. It could be C-SP for site plan 1, site plan 2. You could use 001 or 002. Most architects or engineers use three decimal points on these. And the drawing type, ceiling plans, enlarged plans. Again, you'll see these on some of the samples that we hand out, but this is how, when you look at a paper set of drawings that have been printed out, you look at the title block in the corner down to bottom. If you're looking for architectural drawings, you want to look under the A's. It'll be A101-1 for whatever floor plan happens to be. If you're looking for a landscape plan, it would be listed under L in this case. Some architects and engineers combine civil and landscape together. Depends on who it is, but if you're Harvard University, this is how you want your drawings put in. And if you want to continue to do work with Harvard University, or if you want to continue to do work with University of Maine, you need to supply your material in this format. Otherwise, we're not going to be so likely to hire you again to do work for us. So we can be a little bit tense when it comes to that, because we know that 10 years down the road we're going to need to be looking at these things. Policy on file translation, we don't need to be. So that is the end of this session. I want to go back up to my cover page and just talk for a minute about the syllabus and how we're going to do things this semester. This lecture is our first one. You'll be watching this over the weekend. We'll have already had a meeting in the classroom. We'll look at the syllabus. This class is being done just a little bit differently this year than in the past. In the past, you used a textbook called Fundamentals of Building Construction by Iano, which was basically a building construction textbook. Now, I actually used that textbook in my CIE130 class, so I'm fairly familiar with it. It goes over more to do with actual construction products and pieces, and we'll still have that in here, but I really think that civil engineering graphics should be about how we explain projects graphically, and how, if you're able to draw them, you're also able to read them and interpret them and make them something that you can utilize. And especially for people working for you, having a good background on how drawings are put together, how models are put together. And when we start talking about building information modeling in the second half of the semester with our Revit program, we need to start looking at things beyond two-dimensional and three-dimensional, and actually think about things in four-dimensional and five-dimensional and six-dimensional. And what do I mean by that? Well, with building information modeling, is kind of a concept, like leads and different things with regard to regulations. But building information modeling allows us to add elements. Imagine, if you will, that you want to put a fan unit on the roof of your building. If there is a manufacturer out there that has created a graphic model of that fan unit for Revit or any BIM software, you download it, you put it on your roof, and that has intelligence to the point where it shows what the unit size is in 3 dimensions, shows 2-dimensional elements, but it also has information on maintenance. That could be our 4th dimension. Has information on cost. That could be a 5th dimension. Has information on repair parts, installation manuals, web access. So if 20 years down the road I click on that on a plan, I'm able to get a menu up, maybe right click and say what are the properties of this item I'm looking at, and it would say, well, this is who manufactured it, these are how often you ought to change the belts, these are how often you should change the filters, has a lifespan of 20 years, so you're getting towards the end of the life on this thing, you ought to think about replacing it. With regard to other things that could be incorporated into that, maybe a 7, 8, and 9 9th dimension might be maintenance records. How often have you had to go in and work on that thing? And has that increased over the years to the point where you're spending more money now on it than it's worth, and maybe you ought to think about replacing it with something that's more efficient and better for the environment. Certainly there are times so that with our new work order systems that we're implementing now, facilities, whether you're a hotel or a business or a university, we want to know how much money we're spending on certain things. If something is costing us more than it's worth, it's time to replace it, recycle it. And we get into all of those things with building information modeling. It's something that we're trying to do now in the industry so that in 10 years it will be fully implemented. It'll be like second nature. If I click on a space in a building on this campus, and it will give me information on when was the last time that room was painted, who was the occupant currently, their phone number, what it has on the floor, is there asbestos in the room, is there lead paint in the room, is there PCBs in the room. And that's something we've had to start to deal with lately, is PCBs in caulking from some of our older buildings. Those are the types of things that we're going to be exploring more. So at this point, what I want to do is just show you. Let me get out of this while I'm here. I'll just minimize this. You can look at my desktop. I'm going to go down to my file manager and look at the somewhere Autodesk free educational site. We'll talk about this in the lab anyway. I want people to bring your laptops in with you. But this is just a picture of what it is. It's www.autodesk.com/education/student-software/university/popular. I don't know where the popular comes in. But if you go here, you can download. What you have to do is sign up on the Autodesk site. They'll give you a 3 or 4 year license for the software. You'll see AutoCAD, and you want to download AutoCAD 2014, the basic AutoCAD, and you also want to download Revit 2014 from Autodesk. Both softwares are there. There's other things you can download, but really these are the only two that I'm really concerned about using this semester. Experimentation is in the rest of this is great, but these are the two fundamental programs that we want to deal with, and they have a lot of power. I might be at 5% of the capability of the software, which doesn't seem like much, but Even with a program like MicroStation that I've used for 15 years and do all the 3D models on campus and presentational work, I consider that I probably know about 10 to 15% of that software really well. The rest of it, there's a lot of things in this stuff that can be done, and the only other thing I want to say before I kind of close up here is what we're going to be doing this semester is, for myself, is not redoing things over and over again. We're going to probably start out, our first project will be to create a couple of title blocks with annotation definitions in them. And those are the only title blocks we need to draw all semester, because we'll reuse those over and over as our templates. So we're going to design templates that have title blocks that we can reuse to put our different projects in at different scales. We're going to get those set up so that even though it might seem like a pain to get it set up initially, those are our basic building blocks for the rest of the semester. If we have to do a site plan, if we have to do a building plan, if we're doing a topographical map, we can do them all within that same template file. So creating that template file, getting those things ready, is going to save us a ton of time. And it also means, really for the labs, unless you feel like you're really into it and know all there is to know about AutoCAD, then you can skip it. But attendance to the labs is really important. I know it's not the best time frame. It is for me, but it's not for you, just because I have other work on campus that I have to deal with. So as much as I'd like to be there first thing in the morning, I also have to be there late in the afternoon and into the evening to work on these things. So the structure of the class is going to be, these lectures are going to be on YouTube videos posted on Blackboard, one a week to cover our lecture portion. And then the labs I will be at personally Monday and Wednesday. On the second class, 5 to 7 on Wednesday, will also be an open class that doesn't, if you need some extra help, you want to come in and work, I'll be there to help you. That'll be kind of my open office hours to start with, so that I have that space available. I'll be there. The TAs may be there. We'll be working on things. If nobody shows up, I'll just be working on things that are going to happen next week. But it's a good opportunity to come in and practice and get better with this software. I know what the results need to look like, but again, I'm a little new with Autodesk myself, so I make sure that I practice before I get in there, and I don't make the students do anything that I'm not going to try to do up in front of the class on the projector or over the monitors for yourself. This software is available for Macs. I will tell you, I'm not much of a Mac person, so if you have a Mac, I'll do the best I can with you. Most of the buttons are the same, but there are some differences just because Macs work a little different. And something to think about is that there aren't a whole lot of engineering offices out there that use a Mac-based system. Most engineering offices are PC-based. Not to say there's anything wrong with Macs, it's just I know that Macs are not something that have a lot of design not capabilities, but design applications for the business industry. They do create it for AutoCAD, and that's great. And if you have a Mac, then go ahead and give it a shot. But just keep in mind that it's not one of my. I find that runs a little bit slower on a Mac for most of this software, so we'll see how it goes, but it is available. And with that, I'm going to kind of let you go up for the first lecture portion of this, and on Monday, the 20th, we will get started in earnest. We'll meet for the lab. We'll get started. Bring your laptops with you. Probably the primary thing we want to get done initially is getting the software installed, getting you signed up. They won't send you a lot of crap on your email. It's not like that. They'll sign you up, and they basically I haven't found them to be too bothersome after the fact, so we don't need to worry about that. But it is a little bit tricky getting everything set up correctly the first time, so make sure you get your software installed. You can go ahead and play around with it, do whatever you want, just don't destroy it. And but I wouldn't be too, worst that can happen is you have to reinstall it at this point. But go ahead and play around with it, start doing some of the tutorials, and we'll talk about it more a little bit later on. So good luck, and I will see you on Monday.